Good afternoon, ladies and gentlemen. Welcome to TechGeek webinar series, an endeavor to impart techies. We believe that sharing of knowledge is the key to enhance our skills and grow us as professionals. With this principle in mind, we have initiated a series of webinars conducted by industry experts to give you all a crisp insight of various domains. The topic of today's session is Oracle MAA Best Practices for Oracle Exadata. Our guest speaker today is Manu Goyal, Chief Technology Officer at Heuristics Informatics Private Limited. Known for his technological expertise and versatility, Manu is the backbone of HIPL's boundless technological advantage. With over 14 years of experience in IT, his ability in understanding modern and potential applications for new technologies is outstanding. Extensive experience in working on deployment and integration of several mission-critical database instances in high availability environment like engineered systems, Exadata, ODA, non-engineered systems, and virtualized systems under OVM and VMware. So without further delay, I introduce you all to our guest speaker. Over to you, Manu.
Thank you, Mohini. Good afternoon, folks. I'd like to start by welcoming you all to hopefully the first of many webinars that we're going to be conducting. This particular webinar is titled Maximum Availability Architecture, Best Practices for Oracle Exadata. Over the next 45 or so minutes, I'm going to walk you through how you can implement Oracle Exadata and also take advantage of the high availability and maximum availability concepts available within the Exadata and additionally outside of it. So while we work out through transitioning the slides over to the next one, all right, finally. Okay, so the agenda for this afternoon session is basically, as we said, Exadata and the maximum availability architecture. How does Exadata have high availability, or how does it provide high availability out of the box? What additional configuration best practices can we implement to have a maximum availability implementation for Exadata in place? And then a few reference architectures, very high level, but something that will give you an idea of what capabilities Exadata will have and what else we can do with that. So I guess these pauses will get smaller and smaller as we go along. Right now, it's taking slightly longer than we expected for the slides to transition, but hopefully we will have that sorted out pretty quickly. All right. So a day in the life of Databert. Databert is the fictional data miner for the Dilbert universe. So as you can probably see, I mean, this is what we've tried to do to set the tone for the webinars. But moving on. So while the slides are moving, for those of you who are not aware of what Oracle Exadata is, it is an engineered system created and sold by Oracle. It is basically a rack of several database and storage servers, all engineered together to work in a highly available and extreme performance, as Oracle likes to call it, fashion. The Exadata database has several, or database machine has several different innovations that enable it to provide as much as 10 and maybe even more, 10 times more performance than what you would get on a regular commodity hardware database. While the transition slides move on, and the Exadata database machine typically would have several different configurations, the simplest being what is known as the quarter rack. That quarter rack configuration is 2 database servers and 3 storage servers, all engineered and networked together to work out of the box, which means you buy an Exadata database machine from Oracle. Once they ship it to you, once they come in and install it, it is all ready to go. You are ready to move your databases over there. Typically, what you would see is the Exadata uses Intel-based server, so it is in a fashion commodity hardware by itself, but the way it is set up, it is configured to give you the best possible performance that you can get. The features that allow it to do that, I mean, the configuration of the servers themselves, the software enhancements such as, the way storage is set up, the way storage is, architected would be the right term. And then the underlying InfiniBand backbone of the Exadata system. So as you can see, we've got the database cluster, which is the first piece, which is running Intel-based servers on Linux or Solaris and running database 11G or 12C now. You've got the Ethernet fabric, which is a 10 gig Ethernet fabric that you can use to access the Exadata from your from other servers or from your client machines. And then there's a whole storage grid, which can give you as much as 500 terabytes of raw disk space, plus several terabytes of flash storage. The InfiniBand Network, which is really the one of the most critical pieces of the Exadata machine, is an internal 40 gigabit network. So communication between the internal components of the database machine is blazing fast, pretty much. So one of the other features, I mean, as we said, 2 things that the Exadata database machine does right out of the box is, or one is the extreme performance that it provides you due to the several engineering innovations built into it. The other is high availability out of the box because of the redundancy that is built into the Exadata at every level. I mean, you've got redundant database servers in an active-active configuration. Even in those database servers, every component by itself is redundant, including the power supplies and the fans, the networking components. I mean, the network interface cards, the memory by itself, the storage controllers, everything is redundant. In the storage grid, the data is mirrored across several storage servers. So I mean, depending on what configuration you choose, you can have a double mirrored or triple mirrored storage setup. Then all I/O within the storage servers is redundant. So you are not, one database access request is not blocking another database. So you are not compromising on performance, but being able to put multiple or to put different types of workloads onto the same Exadata machine. And then you've got the redundant network. I mean, every network component on the Exadata database machine is redundant, using either bonded or IPMP configurations. All right. So while the next slide comes up, basically the next slide talks about the various options that we have available for a maximum availability environment for the Oracle Exadata database machine. This includes on your primary data center, you would have capabilities such as the real application clusters that provide scalability and high availability at the hardware level. Then you've got flashback databases, which will allow you to recover from human errors, maybe incorrect data updates, maybe some tables being dropped or some data being deleted by mistake. Right. Then you've got ASM, which handles all your storage, which will allow you to have high availability on the storage side by configuring redundant disk groups or failure groups as they're called. RMAN and fast recovery areas will allow you to have backups that can be put on disk and quickly recovered from if need be. Then you've got online edition-based redefinition, which basically is a new feature of the database 11G release 2, which allows you to keep your database up and running even during maintenance activities such as patching and upgrades. Then these are high availability features only on the local production data center. But for a maximum availability environment, you don't just want to protect yourself from hardware failures, you want to protect yourself all the way from disasters also, which is what is known as disaster recovery, or in other words, business continuity planning. The Exadata in conjunction with the Oracle database and other different software components provides maximum availability features in the form of Active Data Guard or Golden Gate, which will allow you to replicate in near real time all of your production databases over to a remote standby location. So for example, if my primary data center is running in Delhi, I could set up a secondary standby data center running in Mumbai and have the Exadata database machine configured such that all my data updates and data changes in Delhi are replicated over to Mumbai. That way, if for any reason, for example, if there's a fire in my data center and the unthinkable happens and everything is lost, I still have all of my data protected. Why? Because it is available in Mumbai. So what are the building blocks of maximum availability architecture? Basically, maximum availability architecture is not just a hardware or a software piece that we just implement and we're done. And it is a way of pretty much a way of working. So you start with a lot of operational best practices that you should implement. You have several configuration practices and configuration changes that you do to make your maximum availability architecture work, and then there is the actual hardware, the physical and the software logical components themselves. So what are the high availability features of the Oracle Exadata out of the box? So I mean, we're going to take each of those features one by one. We're going to start with storage. One of the biggest things about storage is, even in your typical Oracle databases, you have storage nodes or storage servers in the form of SAN systems such as EMC Square or NetApp, or maybe NAS systems such as Oracle Zone VFS storage appliance. In most cases, what that does is while they will handle some mirroring and some I/O errors and storage checksum failures, what the storage cluster on the Exadata does is it does all of that, plus it performs additional validation on the database blocks itself. So I mean, it is not just checking and repairing corruption on the physical storage medium, but also within the database blocks on the data itself. How it is able to do that is by using the ASM feature of the Oracle database. So the Exadata storage cluster is a bunch of Intel-based servers themselves that are optimized and configured only for the purpose of providing storage, right? In addition, because we're using ASM, we have the ability to create multiple disk groups and multiple failure groups. So what that does is those failure groups and disk groups will allow for disk failures or even full-on hardware failures, and still make sure that your database continues to run while you resolve problems. In addition, the ASM automatically ensures that the disk group placement on the disks themselves is done so as to provide maximum availability, maximum scalability, and maximum performance. So in terms of mirroring and striping, ASM on the Exadata storage cluster will give you probably the best possible configuration for an Oracle database. The InfiniBand Network, as I've said, I mean, the InfiniBand Network is a pretty big piece of the whole Exadata engineered system architecture, the engineering itself. It is a 40 gigabit network that is running on redundant interfaces, redundant HCAs on each component of the Exadata database machine. That includes your database servers, that includes your storage servers. In addition, the switches that are connected to those database and storage servers by themselves are redundant also. So all failures in terms of switch, port, NIC, they are all handled transparently, and the end user doesn't even realize that there is some problem happening. The compute nodes or the database servers themselves, as I said, I mean, the database servers utilize real application clusters and are configured in a high availability configuration, the active. The simplest configuration is the Exadata quarter rack, which has 2 database nodes, all the way up to an Exadata full rack, which has 8 database nodes. In addition, there are features available within the Oracle database software itself that allow us to take advantage of the Exadata, the database machine, and configure redundancies and performance to make best use of the hardware available to us. Performance optimizations, I mean, we can do better memory management using huge pages. We can configure SGA, PGA. We have what is known as instance caging, which we'll probably get to in the next slide. All right, I think we've missed one slide, but basically, as I was saying, we've got instance caging, which allows us to pin a particular database to a number of CPUs on the database servers. For example, your database server may be running a dual 12-core CPU, which gives you 24 cores on per database server. You can have a database, for example, your HR database, pinned to 4 of those cores. So it will only utilize those 4 cores, and only that database will utilize those 4 cores. What does that do? That gives you the independence to have mixed workloads set up on the Exadata without one affecting the other. So you could have a transactional database such as HR with an analytical database such as a data warehouse running on the same database machine without one impacting the other. Now you might ask what that has to do with high availability, but I mean, obviously if you've got heavy data load happening in your data warehouse and if that is going to affect your transactional database, that really is not high availability. So all of these features within the Exadata and in the Oracle database come out of the box, and they make it possible for you to consolidate your databases and ensure that each line of business or each business group is able to work independently without one affecting the other. In addition, there are what is known as automated health checks built into the Exadata. There is a script that can be scheduled to run, which is called Exacheck. It is a very, very comprehensive configuration check of the entire Exadata software and hardware. Basically a 100-point check that will spit out a pretty large HTML file giving you a rating out of 100, how many points you scored and what are the areas that need attention. It could be anything in the InfiniBand network to the database nodes to something specific on the database nodes themselves. For example, a particular memory DIMM has failed or is not working properly. So it will give you all of that information in there. It also reports any variances that you may have from standard MAA best practices, and suggests any configuration changes or corrective measures that we should be taking. Typically, you would want to run it on a monthly or a bi-monthly basis, and also every pre and post maintenance session, every patching session, every database upgrade session, you would want to run it before and after just to make sure that the maintenance has completed successfully and has not affected any of your databases. Configuration best practices. Typically, what would you want to make sure, or how would you want to ensure that you are in a compliant best practices environment with respect to maximum availability architecture? So, as I said before, I mean, configuration best practices, they start with operational best practices, then configuration, and then well, I mean, the other way around with your hardware, software components, and then your configuration practices, and then your operational best practices. We are going to be concentrating in this slide deck on just the configuration best practices, which would include storage, the network, the compute nodes, how you should set up backups, disaster recovery, and how you should deal with corruption either on the database blocks or on the physical storage mediums. So For the storage servers, I mean, how do you handle, how do you set up MAA for the storage servers? Typically, in a storage environment, as I said, I mean, the storage servers use automatic storage management, which is ASM, and you would want to configure at least 3 disk groups within the storage servers. Data which would have all of your database data files, RECO or log, which will contain all your recovery files, fast recovery area, your archive logs, and then your DBFS, any file system related data that you need to store. For example, data pump exports, something. I mean, that's an ideal example of what you would want to store in a DBFS environment. Typically, your ASM would be configured in either a normal or a high redundancy. High redundancy obviously is always recommended. A high redundancy setup will give you triple mirroring in terms and will provide protection against multiple points of failure at the same time. How does that happen? That happens because high redundancy will set up at least 3 different failure groups for each disk component. In addition, ASM has built-in features to for intelligent detection and elimination of file system and data block corruption. So, I mean, it will continuously monitor, detect, and fix corruption in either the data block or in the file system itself. Now, I mean, assuming we are going with a full-blown maximum availability architecture, and if you're using data guard also, I mean, you can go with a normal redundancy environment, but again, high redundancy is always recommended. So, how should you configure, or what should you configure disk in the ASM disk groups? So, as we said, high redundancy is what we should be shooting for all the time. Why? Is because of what you can see on your screen right now. I mean, in terms of dual storage failures, for example, you may have 2 storage nodes or 2 disks that fail at the same time. It is admittedly a rare possibility, but it does happen. So, in a normal redundancy, because you have only a single mirrored environment, if 2 disks fail, there is a very high possibility that you will lose some data. In this particular case, because you have a triple mirrored environment, you will protect yourself against the loss of a disk group or a cluster. If we are going through a planned maintenance session which causes storage failures, a high redundancy environment will be able to protect you from that, and you will be able to recover from it. At the very least, I mean, we should try to have high redundancy at least in one of the 3 recommended disk groups. If we set the data disk group to a high redundancy, we have the applications and the database that remain available with multiple storage failures. On the other hand, I mean, depending on SLAs and individual or organizational needs, we can keep data at a normal redundancy, but the recovery disk group at a higher redundancy. That way, we will have a higher recovery time objective. That is, if 2 storage or 2 disks fail, we may lose a disk group, but we'll be able to recover with 0 data loss. So our recovery point objective will be 0, but our recovery time objective will be a little higher than what you would see in a high redundancy on the data disk. So compute nodes or database nodes. Typically, Oracle Database 11g has clustering features that are far matured from their older predecessors. Typically, you would have what is known as a scan address for an Oracle database 11G cluster or a release 2 cluster, which provides transparent failover from database node failure. So if you have, because your clients see only a single scan or a single cluster address, they don't even know that at the back end they're running more than one database nodes, which also means that if one of those nodes fails, the application itself remains unaware. Obviously, we would want to make sure that our fast start mean time to recovery target is configured properly to be able to meet our SLAs. Obviously, the lower that we set the MTTR target to, the more complicated the configuration will be. At the very least, we will have a few minutes worth of mean time to recovery that we will have to contend with. Client connections can be configured to take advantage of automatic node failover using features of the fast application notification and transparent application failover. So FAN, the Oracle database transmits FAN events which the applications can listen for and automatically fail their database connections over. So if, for example, a database node were to fail, the Oracle database would send out FAN notifications to the applications, for example, your WebLogic servers, and your WebLogic servers would be able to handle those notifications and fail over the data connections to the remaining nodes. Resource management. As I was saying, there are several resource management features available, some that are specific to the Oracle Exadata database machine, others that are configurable within the Oracle database. Excuse me. So using use pages, we can ensure that memory management is optimally configured. It allows us to use large memory areas for database instances to enable several terabytes worth, several terabyte sized databases, or even several petabyte sized databases to run very, very smoothly. Instance caging, on the other hand, as I was telling you earlier, we can limit the amount of CPUs that are used by an Oracle instance. So that allows you to run mixed workloads on the Oracle Exadata database machine. The database resource manager is for you to be able to allocate CPU resources across multiple services. So instance caging will allow you to allocate CPUs across multiple databases or multiple instances, and the DBRM will allow you to further allocate those CPU resources across multiple services that might be running in the same database. And then IORM, or the IO resource manager, allows you to configure IO bandwidth in such a way, or distribute IO bandwidth across different databases. So for example, you can configure your data warehouse database to be optimized for read IO, because that's primarily what its function is going to be. Whereas your OLTP databases or your HR database, for example, can be configured for a higher write IO. Its primary function is. So that way you are optimizing the limited IO resources available within the Exadata database machine. The resources available within the Exadata are much higher than what you would see in a typical database cluster. However, they are still limited. So making the most optimum and the best use of those resources is what the IORM will allow you to do. Configurations that can help us allow detect, prevent, and repair data corruptions. I mean, these are all features of the Oracle database itself that can detect physical corruption within the database. And if the physical corruption does happen, it can repair that corruption automatically. Similarly, with the logical corruption, you can have corruption detected and automatically repaired. In addition, if we are using DataGuard or Active DataGuard for disaster recovery to a standby environment or standby data center, that Active DataGuard will be able to automatically repair corruptions at the block level on disk. So fast recovery, what is flashback? Flashback, as the name suggests, is the capability of the Oracle database to go back in time. So if, for example, as part of a maintenance activity, a DBA were to, by mistake, drop a table, or if a developer or if an end user by mistake deletes some data that did not need to be deleted. Now the data has, the delete transaction has already been committed. So our traditional thinking or traditional knowledge says that once a transaction has been committed, that's it, you're done. So if you delete, you commit. As long as you don't commit, you can roll back. But once you commit, you're finished. Not anymore. Oracle database will allow you to go back in time, to flashback to a time before the delete transaction ever happened and recover that data. Now you can flashback a transaction, you can flashback a table, you can run a simple select query back in time. So do a select star from table as on a date and time, right? Or you can flashback an entire database and push the database back to a point in time, say 3 hours ago. Obviously, that will require that you configure your flashback and provide enough storage for flashback to be set up. So what flashback does is it will have a minimal impact on OLTP and DW workloads as long as you make sure that you are maintaining operational practices. The only thing that really needs to be taken care of when setting up flashback is the size of the fast recovery area. Your fast recovery area needs to be configured to be able to hold the flashback for as long as you want it to be. So for example, if you want to be able to flashback your database to say 5 hours back in time, right? You have to be able to, you have to have enough storage on disk to store at least 5 hours of flashback data on the disk. How do you do that? By setting up the recovery size through simple calculation, which is how long your redo files have, or how much redo is getting generated per hour multiplied by the flashback retention target that you have, 5 hours. So if, for example, we're generating 50 gigabytes of redo every hour, right? Then 50 into 5, you want to have at least 250 GB available on your fast recovery area. Backups. So there are several different backup options available. The Oracle database comes out of the box with what is known as Recovery Manager, which is RBAN, which will allow you to back up to disk on in the fast recovery area, and then also allow you to incremental backups. Right? Then there is an additionally licensable software which is called the Oracle Secure Backup, which will be able to handle the entire backup lifecycle. It will allow you to set up scripts that will automatically back up databases and put them onto tape or put them onto disk and tape, and also manage your backup retention requirements and everything. What are the options that we have available for backup? I mean, destinations you can store backups within the Exadata storage itself, within the DBFS. You could do that with your RMAN backups as well as your data pump exports. Non-Exadata disk storage. So if you have an additional storage server, for example, the SAN, such as the ZFS appliance or an EMC or NetApp filer, you can move your RMAN backups to those storage nodes or storage mediums. And then you can have a third-party tape library set up that can back up your databases to tape. So backup destination options, as we were talking about earlier, you have the storage, the Oracle Exadata storage itself. I mean, if you're running out of storage within the storage servers, there are storage expansion racks available that can, you know, as the name suggests, expand your storage. Then you have the ZFS storage appliance that can act as your external storage medium, where you can back up all your database, non-database files, as well as use it for other things like snapshots and clones. And then you have tape libraries where you can configure offsite backups and long-term retention of your databases. Depending on what technologies or what products you use for each of these things, you can use either the 10 gigabit network or the InfiniBand network for setting these things up. For example, if you were to use the ZFS storage appliance, that can connect to the Exadata via the InfiniBand network, which reduces your backup time significantly because it uses a 40 gigabit network versus a 10 gigabit network. Similarly, with an Oracle tape library, I mean, it's all the same concept. Disaster protection or disaster recovery. So this is one of the key components of a maximum availability architecture. Typically you would have a production database in your primary data center, and you would have something like the Oracle Data Guard or Oracle Active Data Guard running on an active, on a standby environment in a remote location. How this works is it continuously mines, ships, and applies the redo logs from the primary database to the standby database. And then there's a third-party component called the Data Guard Broker, which is continuously monitoring both production and standby and can detect when there is a full failure of your production environment. When that happens, the Data Guard Broker automatically switches over to the standby database and reconfigures it or repurposes it to be the new production. While that does not happen, I mean, when everything is working just fine and your production database is running, you can at the same time, for additional availability features, segregate your workload between the production and the standby database. With your production workload, as in the transactional features of your application, can be running on the primary production database, whereas read-only queries, reports, they can run on your active standby database. That way, heavy reports do not impact users entering transactions. So the performance and the availability is as best as you can expect. All right, so what best practices should you consider when you want to configure Data Guard? So primarily, the Data Guard is a very network intensive process, obviously, because it is going to be shipping redos to your standby environment. So the biggest or the most important thing to consider is how to configure the network to allow for optimum data guard transport. Network would mean both of those two things, the actual network itself and the Oracle's net services. We should optimize to be able to handle the necessary redo transport. Additionally, we should make sure that the redo log groups are configured and set up on the fastest portion of the storage, which is the flash storage. Why? Because obviously that will reduce lag in terms of I/O. The second aspect of tuning data guard is to make sure that the apply on the standby database is happening optimally. We can use different Oracle database monitoring features to identify how the apply performance currently is and tune the coordinator and the recovery slaves to optimize that performance. Additionally, we can use a specific feature of the Oracle Exadata database machine, which is called the hybrid columnar compression. What that does is it stores data on the disk in a compressed format and does it on the fly transparently. So the end user does not notice any significant performance impact of the columnar compression. However, there is up to a 78% reduction in the volume of redo and network that gets utilized, which obviously means that your apply or your transport is much faster because there's a 78% reduction in the amount of data that needs to be transported from one side to another. All right, so how do we configure data guard for automatic client failover? So using the server control features of the clusterware, we can set up the standby database or the standby site as a physical or a snapshot standby, depending on what we choose it to be. And then we can configure the data guard broker, which is required for complete automation, to detect failures on the primary database and automatically switch the standby database role to a primary. The data guard broker also issues FAN notifications so that your applications that are FAN compliant can automatically and transparently fail over to the standby database. This is typically how you would, sorry about that, this is typically how you would configure connection parameters or TNS names parameters on your client applications. So as you can see, we've got multiple descriptions set up first for the primary, which is the, as you can see, the Austin scan, and then for the secondary, which is the Houston scan. So between the two descriptions, we've got load balancing disabled because obviously data guard does not allow for load balancing, but failover is enabled, which means if an application attempts to connect to the primary database is unable to do so, it will automatically fail over to the secondary application, which is the standby database. Reference configurations. As I said, I mean, at the end of the webinar, we would go to have some sample reference configurations of what are the various architectures that we can have set up. So simple high availability, I mean, it is called MAA, but I would say it is MAA with a local disaster recovery. the primary database and the standby database are within the same geographical region, so within say 200 miles of each other. So you've got an high availability engineered system, Exadata running on the primary database, another high availability engineered system running on the standby database. And there's a synchronous reroute transport between the two primary and the standby database. Data guard is configured for maximum availability. Second would be a true remote or a disaster recovery environment where you've got, again, Exadata engineered systems running on both environments, but the standby environment is in a completely separate geographical region to help protect against natural disasters in addition to anything else. Your redo transport is asynchronous, so your data guard is configured for maximum performance with the understanding that the asynchronous transport will move all your data over to the remote location. However, your recovery time objective would be higher than what you would see in a local DR. And then this is basically the best of all worlds. I mean, you have a local standby database that is configured for synchronous transport, and then you also have a remote standby database that is configured for asynchronous transport. What this does is it gives you protection against local data center or data hardware failures by quickly switching applications over to the local standby environment. But it also protects against natural disasters by allowing you to have a slightly higher RTO and RPO, but be able to protect your database and your data and be able to move to this remote standby location. This brings us to the end of the webinar. I hope this was useful to you. We are open to questions at this point. I guess the moderator is going to be sending questions out to me, so whenever you guys are ready.
Thank you so much, Manu, for this session. I would request all the audience to start sending their questions to me so that I can forward them to Manu, and we can begin with the Q&A round. We have a question now. Are you able to see it?
Just a second, please. I'm pulling it up. All right, so we have a question from Rahman J. Sheikh about how Exadata hybrid compression can save a lot more storage to client compared to OLTP high compression feature available within the normal 11G installed system. So two things. The biggest thing to remember is that the hybrid compression is actually hybrid columnar compression. So how compression works is in the 11G installed system, the database will compress data in the form of rows, in the form of tuples. Right? In a hybrid columnar environment, in the Exadata environment, the column data is compressed, which is likely to be far more common. So the compression ratio that you receive, is much higher. In addition, because of the optimizations built into the storage itself, the compression can be made, the compression algorithm that is used can be even higher, but it can be transparent to the end user. So it can use a, how should I put it? Let me back up a bit. It can use a more complicated algorithm, but because it is optimized for something like that, the end user does not feel the impact. I don't know if that made much sense. I'm going to see if Sandeep, I've got a panelist here with me, Sandeep, who can help out with this. All right. So while Sandeep comes back, Rahman's come up with another question. Can we have a non-Exadata system at the DR? Yes, you can. However, again, when we're talking about best practices, you would typically want to have an Exadata environment on the DR site also. Plus, there will be certain limitations. So, for example, if you're using features like hybrid columnar compression, as we talked about, you may or may not be able to utilize a regular, how would you say, non-Exadata environment there. But in most cases, yes. Depending on cost and budgets, you could have a non-Exadata environment on the DR site. So any other questions?
We have one more question. If you could see.
How to check? Yeah. Pratibha Pal, how to check Exadata health check? So as I was, while we were going through the webinar, there were a couple of things that we talked about. There's a utility built into the Exadata system itself, which is called Exacheck. You run an Exacheck script, it will collect information about all of the different components of the Exadata system, right from the PDUs, which are the power distribution units, all the way up to the database software itself, database and storage software. It will generate an HTML-based report, which will grade your environment on a 100-point scale. Additionally, for continuous monitoring, typically you would want to have an enterprise manager, grid controller, cloud control environment that is monitoring your environment for alerts, so that any failures can be proactively detected and resolved.
Well, those were the only questions we had, I guess. Thank you so much, Manu, for answering the questions.
Thank
I'm
you.
really thankful to you for conducting this webinar. I would also like to thank our participants for the support in making this webinar a success. I would like you all to know that the recording of this webinar would be available on techgeek.com by tomorrow. Thank you all. Have a great evening.
Thank you.
Thanks. Bye.